Okay, so this is the video for the lesson on November 5th, I believe, where we talked about how to calculate percentage composition theoretically and experimentally, and this is important for the lab that we are going to do very soon. So we are given some data here, so we're going to write that down first. So mass of crucible we can weigh, and we take the before measurement, and that's 16.94 grams. Then we put our magnesium on the crucible, and that's 17.33 grams. And after we complete the experiment, this is the product that's formed, magnesium oxide, and that would be 17.47 grams. Now these come from observations, so I will give them to you if you're calculating them, or they will be provided, or you can actually measure them when you're doing your calculations. So we get our mass of Mg by doing, or magnesium, by doing 17 minus 16.94, which turns out to be 0.39 grams. Mass of magnesium oxide is 17.47 minus 16.94. You can see that I'm just subtracting the mass of the crucible from this value and this value to get my magnesium and my magnesium oxide values. So this was 0.53 grams. And so my mass of oxygen was magnesium oxide minus magnesium. 0.53 minus 0.39, which is 0.14 grams. So what observations about proper lab procedure can you make? You must make sure to not spill any reactants, wear lab coats and goggles or eye protection so that you can don't get injured especially when doing labs that involve a Bunsen burner or heat. And we could have observed how to set up a stand to heat up things in a crucible. So you set up your little you have your stand first of all, and then you have your circular device, then you have your little triangle in which you can place the crucible in, and then put the substances here. The Bunsen burner can be below, and like that. So we'll hopefully see this again so that we can go through it in more detail. But let's go out and then scroll down. So our experimental percentage composition uses actual masses. So our percent of oxygen was the mass of oxygen divided by mass of the total, which was 0.14 divided by 0.53 times 100%, which turns out to be 26.42 roughly percent. And percent magnesium is the same calculation. But notice here that when we're calculating experimental, we are using the experimental values, the values that we actually measured, and not any other periodic table molar mass values that we would usually use to calculate these things. So 0.39 divided by 0.53 is 73.5, which both of them add up to 100, so that makes sense. For a theoretical percentage composition, we use molar masses from periodic table, right, to calculate our percentage composition. So we're going to do essentially the same thing, but instead of mass, we're going to say molar mass of oxygen divided by molar mass of MgO. Molar mass of oxygen we know is 16.00 divided by, let's find the molar mass of magnesium oxide, which is 24.3 plus, well, 16.0 on a less accurate periodic table. So 24.3 plus 16.0 is 40.3, so that's our total. And so if we do this and multiply by 100%, we get 39.7% oxygen, and our percent magnesium would have to be molar mass of magnesium divided by molar mass of magnesium oxide, which is 24.3 divided by 40.3 times 100%, which is, let's see, 60.3%. Again, both of those add up to 100, so that works. And lastly, we will calculate percentage error, which is, we will use the formula in our formula sheet. It's experimental minus theoretical divided by theoretical. You could also say theoretical minus experimental, that's fine. And because we're writing a percent value, we're going to say times 100%. So experimental, we can do either oxygen or magnesium. It doesn't have to be both, but we're just going to take oxygen for the sake. So experimental was 26.42. Our theoretical was 39.7. Divide that by 39.7, times that by 100%. And we have a percent error of negative 33.45%. So that was our percent error. Where did this error come from? We spilt some reactant on the table, or our reaction may not have been complete. There are many reasons for the error, or there could have been side products formed, such as magnesium nitride is a common side product formed during the burning of magnesium. Instead of magnesium oxide, you get magnesium nitride because there's a lot of nitrogen in the air. So those were some of the sources of error. So hopefully the important thing was in this to calculate, experimental percentage composition uses actual masses, theoretical percentage composition uses molar masses on the periodic table, and to calculate the percent error we used this formula and calculated the percent error. Just want to check whether I have that formula correct. Hopefully I do. I lied. It's theoretical minus experimental. So we'll just flip these. Values and make this 39.7 minus 26.4, which will give us the same value, right? Doesn't matter which one we subtract from the other, just a negative or positive sign. So some experimental values are bigger, some experimental values are smaller than theoretical value. That depends on what experiment you're doing. So either formula would be acceptable, but on your formula sheet it is, in fact, theoretical minus experimental. So I apologize for the mistake here. All right, so I will see you guys later in class.